Good day, ma'am. I am Joseph D. Machado Jr. from BCE 1B. Let's turn the topic, Lecture 6, Fluid Dynamics. Problem set. Question: what is a fluid? In physics, the definition of a fluid is more specific. Here, fluids refer to any material that cannot withstand a tangential shearing force and is constantly changing shape in response to said shearing force. Means, ang mga likido ay karaniwang itinuturing ng mga bagay na dumadaloy at umaayon upang punan ang kanilang kapaligiran. Sa physics daw, ang kahulugan daw ng likido ay tiyak daw. Dito daw ang tumutukoy sa anumang material na hindi makatiis sa tangential shearing force at patuloy na nagbabago ng hugis bilang tugon sa nasabing shearing force. Then sa hydrodynamics is the study of movement of fluids. When discussing fluids, it is first important to understand that the term fluid is an umbrella category that includes both liquids and gases. Ibig sabihin, ang hydrodynamics ay pag-aaral ng paggalaw ng mga likido. Unang-una, mahalagang manawaan ng terminong likido ay isang kategorya ng payong na kinabibilangan ng parehong mga likido at gas. Ang ideal fluid is a fluid with negligible viscosity. Ibig sabihin, ang perpektong likido ay isang likido na may hindi gaanong lagkit. In viscosity is a measure of internal friction in a fluid. We examine it is more detailed in viscosity and turbulence. Ang lagkit ay isang sukatan ng panloob na friction sa isang fluid. So, we examine it more detailed in viscosity and turbulence. In a few examples, we examine an incompressible fluid, one for which an extremely large force is required to change the volume since the density in incompressible fluid is constant throughout. Ibig sabihin, isa kung saan ang isang napakaliking puwersa ay kinakailangan upang baguhin ang volume dahil ang density sa isang hindi mapipigil na likido ay pare-pareho sa kabuuan. Yun lang. Continue number 2, example 14.1, page 693.694. Question: what force must a dam withstand? Consider the pressure and force acting on the dam retaining a reservoir of water. In figure 14.7, suppose the dam is 500 meter wide and the water is 80 m or meter deep at the dam as illustrated below. A. What is the average pressure on the dam due to the water? And B. Calculate the force exerted against the dam. The average pressure P due to the weight of the water is the pressure at the average depth, height of 40 m. Since pressure increases nearly with the depth, the force exerted on the dam by the water is the average pressure times the area of contact force is equals to PA. Solution: A. The average pressure due to the weight of a fluid is P. Pressure due to liquid is equals to height of liquid above that point times liquid of density times gravitational field strength. Entering the density of water from table 14 0.1 and taking height to be the average depth of 40.0 meter, we obtain pressure due to liquid is equals to the quantity 40.0 meter times the quantity 10 cube kilogram over m cube, the quantity 9.80 m over s squared. So we are going to manipulate. So the answer is 3.92 times 10 raised to the power of 5 n over m cube. So substitute. So the answer is 392 kilogram pascal. B, we have already found that value for P. The area of the dam is 392 kilogram pascal. So area is equals to 80.0 m or meter times 500 meter. So the total of area is 4.00 times 10 raised to the power of 4 m squared. So that force is equals to the quantity 3.92 times 10 raised to the power of 5 Newton over a per m squared multiplied by 4.00 times 10 raised to the power of 4 m squared. So we're going to substitute. So the answer is 1.57 times 10 raised to the power of Newton. Although this force seems large, it is small compared with the 1.96 times 10 raised to the power of 13 Newton weight of the water in the reservoir. In fact, it is only 0.08% of the weight. Ibig sabihin, bagamat tila malaki ang puwersang ito, maliit ito kumpara sa 1.96 times 10 raised to the power of 13 Newton na bigat na tubig sa reservoir. Sa katunayan, ito ay may 0.800% lamang ang timbang. Question number 3. Example 14.3, page 705 to 707. Question. Calculating force on wheel cylinders. Pascal puts on the brakes. Consider the automobile hydraulic system shown in figure 14.18. Suppose a force of 100 Newton is applied to the brake pedal, which acts on the pedal cylinder, acting as a master cylinder. Through a lever, a force of 500 Newton is exerted on the pedal cylinder. Pressure created in the pedal cylinder is transmitted to the four wheel cylinders. The pedal cylinder has a diameter of 0.500 cm and each wheel cylinder has a diameter of 2.50 cm. Calculate the magnitude of the force sub 2 created at each of the wheel cylinder. We are given the F sub 1 applied to the pedal cylinder. The cross-sectional areas A sub 1 and A sub 2 can be calculated from their given diameters. Then we can use the following relationship to find the F sub 2
So this is the value F sub 1 over area sub 1 is equals to F sub 2 over area sub 2. So we're going to manipulate the algebraically to get F sub 2 on one side and substitute known values. So, solution. Pascal's principle, a principle applied to hydraulic systems, is given by F sub 1 over A sub 1 is equals to F sub 2 over A sub 2. So this is the formula of F sub 2 is equals to area sub 2 over A sub 1. F sub 1 is equals to pi radius square over pi r square sub 1 F sub 1. So our A sub 2 is equals to 1.25 centimeter square over our A sub 1 is 0.250 centimeter square multiplied by F sub 1 is 500 Newton. So we're going to manipulate. So we're going to substitute. So this is the answer. The F sub 2 is equals to 1.25 times 10 raised to the power of 4 Newton. Then this value is the force exerted by each of the 4 wheel cylinders. Note that we can add as many wheel cylinders as we wish. If each has a 2.50 centimeter diameter, each will exert 1.25 times 10 raised to the power of 4 Newton. A simple hydraulic system, as an example of a simple machine, can increase force but cannot do more work is done on it. Work is force times distance and move, and the wheel cylinder moves through a smaller distance than the pedal cylinder. Furthermore, the more wheels added, the smaller the distance each one moves. Many hydraulic systems such as powers, brakes, and those in bulldozers have motorized pump that actually does most of the work in the system. Means, ang halagang ito ay puwersa na ginagawa ng bawat isa sa 4 na silindro ng gulong. Tandaan na maaari kaming magdagdag ng maraming mga silinder ng gulong ayon sa gusto natin kung ang bawat isa ay may diameters na 2.50 cm, bawat isa ay gagawa ng 1.25 times 10 raised to the power of 4 Newton. Isang simpleng hydraulic system bilang isang halimbawa ng isang simpleng makina maaaring magpataas ng puwersa ngunit hindi makagawa ng higit na trabaho kaysa sa ginagawa dito. Ang trabaho ay oras ng puwersa, inilipat ang distansya at ang silindro ng gulong ay gumagalaw sa isang mas maliit na distansya kaysa sa silindro ng pedal, at saka kung mas maraming gulong ang idinagdag, mas maliit ang distansya ng ginagalaw ng bawat isa. Maraming hydraulic system gaya ng power brakes at mga bulldozer may motorized na bomba na aktwal na gumagawa ng halos lahat ng gawain sa system.
In number 4, example 14.4, page 710, calculating average density. Suppose a 60.0 kg woman floats in fresh water with 97.0% of her volume submerged when her lungs are full of air. What is her average density? Strategy. We can find the woman's density by solving the equation This one, fraction submerged is equals to P object over PFL. For the density of the object, this yields P object is equals to P person is equals to multiplied by fraction submerged times PFL. We know both the fraction submerged and the density of water, so we can calculate the woman's density. Solution. Entering the known values into the expression for her density, we obtain P person is equals to 0.970 times the quantity 10 cube kilogram divided by m cube. So we're going to substitute and multiply. So the P person answer is 970 kilogram over m cube. Significance: the woman's density is less than the fluid density. We expect this because she floats. Numerous lower density or substances float in higher density fluids, all in water. A hot air balloon in the atmosphere, sa taas, sa ibabaw sa air, a bit of cork in wine, an iceberg in salt water, and hot wax in a lava lamp, to name a few. A less obvious example is mountain ranges floating on the higher density crust and mantle beneath them. Even seemingly solid earth has fluid characteristics. For measuring density, one of the most common techniques for determining density is shown in figure 14.23. An object, here a coin, is weighed in air and then weighed again while submerged in a liquid. The density of the coin, an indication of its intensity, can be calculated if the fluid density is known. We can use this same technique to determine the density of the coin is known. All of these calculations are based on Archimedes' principle, which states that the buoyant force on the object equals the weight of the fluid displaced. This, in turn, means that object appears to weigh less when submerged. We call this measurement the object's apparent weight. The object suffers an apparent weight loss equal to the weight of the fluid displaced. Alternatively, on balances that measure mass, the object suffers an apparent mass loss equal mass of fluid displaced. Number 5. Example 14.5, page 714 to 715. Calculating fluid speed through a nozzle. Question. A nozzle with a diameter of 0.500 cm is attached to a garden hose width of 0.900 cm. The flow rate through hose and nozzle is 0.500 liters per second. Calculate the speed of the water, A in the hose and B in the nozzle. So we're going to strategy. We can use the relationship between flow rate and speed to find both speeds. We use the subscript 1 for the hose and 2 for the nozzle. Solution. We solve the flow rate equation for speed and use pi r sub 1 square for the cross-sectional area of the hose cross obtaining. So this is the value. Velocity is equals to Q over A is equals to Q over pi r square sub 1. Then substituting values and using appropriate unit conversions yields. So our
Q velocity is equals to 0.500 liters per second multiplied by 10 negative cube m cube per liters over 3.14 multiplied by 9.00 times 10 negative cube m square. So we're going to substitute, multiplied, then the answer of the velocity is 1.96 meter per second. And B, we could repeat this calculation to find speed in the nozzle V sub 2, but we use equation of continuity to give a somewhat different insight. The equation states A sub 1 V sub 1 is equals to A sub 2 V sub 2. Solving for V sub 2 and substituting for pi r square for the cross-sectional yields. So V sub 2 is equals to A sub 1 over A sub 2 V sub 1. So answer is pi r square sub 1 over pi r square sub 2. V sub 1 is equals to r square sub 1 over r square sub 2 V sub 1. Substituting known values, V sub 2 is equals to the quantity 0.900 centimeters square, kaduahon nato, then over 0.250 centimeter, kaduahon gyapon siya, then ato siya i-substitute, multiplied, then 1.96 meter per second. So we're going to substitute all this equation. The V sub 2 answer is 25.5 meter per second. Then the significance, a speed of 1.96 meter per second is about right for water emerging from a hose with no nozzle. The nozzle produces a considerably faster stream merely by constricting to flow to a narrow tube. The solution to the last of the example shows that speed is inversely proportional to the out of a candle at quite a distance. For example, by pushing our lips where areas blowing on a candle with our mouth wide person is quite ineffective. The last number 6 example 14.7 page 720 to 721. Calculating pressure of fire hose nozzle. Question. Fire hoses used in major structural fires have an inside diameter of 6.40 cm. Figure 14.33. Suppose such a hose carries a flow of 40.0 liter per second, starting at a gauge pressure of 1.62 times 10 raised to the power of 6 Newton per m square. The hose rises up 10.0 meter along a ladder to a nozzle having an inside diameter of 3.00 centimeter. What is the pressure in the nozzle? Strategy. We must use Bernoulli's equation to solve for the pressure since depth is not constant. Solution. Bernoulli's equation is P sub 1 plus 1 over 2 PV 2 over 1 plus PGH. is equals to P sub 2 plus 1 half PV square sub 2 plus PGH sub 2, where subscripts 1 and 2 refer to the initial conditions at ground level and the final conditions inside the nozzle respectively. We must first find the speeds V sub 1 and V sub 2 since Q is equals to A sub 1 V sub 1. We get V sub 1 is equals to Q over A sub 1 is equals to 40.0 times 10 negative cube m cube per second over pi multiplied by 3.20 times 10 negative square m square. So we're going to substitute. So the answer of V sub 1 is equals to 12.4 meter per second. Similarly, we find V sub 2 is equals to 56.6 ml. This rather large speed is helpful in reaching the fire. Now, taking H sub 1 to be 0, we solve Bernoulli's equation for P sub 2. P sub 2 is equals to P sub 1 plus 1 half P plus 1 half P, the quantity V square sub 1 minus V square sub 2 minus PGH sub 2. Substituting known values yields P sub 2 is equals to 1.62 times 10 raised to the power of 6 Newton per m square plus 1 half multiplied by 1000 kilogram per m cube bracket multiplied 12.4 meter per second square minus times 56.6 meter per second square bracket negative minus times 1000 kilogram per m cube times 9.80 meter per second square times 10.0 meter. So we're going total of this equation. So the P sub 2 is equals to 0. Significance: this value is a gauge pressure. Since the initial pressure was given as a gauge pressure, thus nozzle pressure equals atmospheric pressure, as it must, because the water exits into atmosphere without changes in its conditions. That will be all. Thank you.